Pluto is a long way away from the Sun, of course, so the Sun is about 1,500 times fainter than it is here on Earth. So, it's very cold. Temperatures drop to around minus 230 degrees Celsius during the night time. In a heat wave, you might get as high as 170 degrees Celsius. It has a very tenuous atmosphere as well. Welcome, curious minds, to an exploration beyond the familiar realms of our solar system. What if I told you that Pluto, the distant and enigmatic dwarf planet, is finally making its cosmic move, potentially colliding with none other than Neptune, the ice giant? Pluto's rebellious nature has been evident from the beginning, a renegade on the fringes of our celestial neighborhood. Its orbit audaciously crossing paths with another planet challenges the conventional norms of planetary behavior. I mean, that's no kind of conduct for a planet, right? From the perplexing intricacies of Pluto's orbit to the raised concerns voiced by astrophysical luminaries like Tyson and Koku, a lingering question hangs in the cosmic balance. Will these celestial giants engage in a collision course? Could the convergence of their paths spell unforeseen consequences for our beloved planet Earth? Today, we embark on a cosmic journey filled with uncertainty. While the answers to these celestial queries may elude us at the moment, the potential for a collision of such cosmic proportions serves as a stark reminder that the universe is a stage for events both awe-inspiring and perhaps a touch on the terrifying side. Join us as we delve into the mysteries that orbit our understanding of Pluto and Neptune, contemplating the possibilities of a celestial clash that could reshape the cosmic balance of our solar system. The stage is set, and the unfolding drama beckons us to witness the enigmatic dance of the planets. Among other potential space disasters, the cosmos harbors an array of enigmas, and among them is the intricate puzzle known as the three-body problem. Yet scientists foresee other potential cataclysms within the celestial theater. Although a planet colliding with another in space is highly unlikely, it is not totally out of the question. Gravitational interactions, as described by the three-body problem, are one of the forces that affect planetary orbits. An example of a space system where gravitational forces produce a periodic pattern known as orbital resonances is TRAPPIST-1, which has 7 planets the size of Earth. As time passes, these patterns might weaken planet orbits, increasing the likelihood of collisions. The current situation does not include any collisions, even though systems such as TRAPPIST-1 are very dense and planets impact each other's courses, especially when they are close. Scientists regularly monitor these systems to understand this. With this information, we can better understand how the planets move through space. Another unknown known component is rogue planets, which float aimlessly in space rather than in orbit around a star. Expulsion of planets from star systems can occur as a result of gravitational poles or other astronomical phenomena, such as another star's close approach or dynamic instability in systems with more than one planet. As time passes, these roving planets have the ability to travel great distances, possibly even reaching areas far from where they began. It is possible that they will cross paths with other star systems on their solo voyage. The possibility of a planet-planet collision increases if one of these planets travels to another solar system. Nonetheless, a rogue planet striking another planet head-on is quite unlikely, considering how vast and mostly empty space is. The sparsity of planets in open space and the immensity of interstellar distances work together to discourage frequent collisions. It is already highly unlikely that 2 rogue planets will collide, but the frequency of rogue planets is far lower than that of stars and planets in stable orbits. The star systems involved can become chaotic in the event of a galactic merger. It is highly improbable that planets will collide head-on during these cosmic events due to the vast interstellar distances. The orbits of stars and planets within merging galaxies are altered dramatically by the strong gravitational forces. A planet may become a renegade world, freed from any star when this kind of chaos forces it out into the cold black depths of intergalactic space. On the other hand, planets could be expelled from their orbits, collide with one another, or even impact their host stars as a result of these gravitational disturbances. When gas and dust are compressed under extremely high pressure, gravitational rearrangement can actually cause new celestial bodies to form or perhaps start stars to emerge. In our solar system, the late heavy bombardment suggests that around 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This surge in impact is believed to have resulted from gravitational disturbances caused by the outer planets. During this chaotic phase, gas giants such as Jupiter and Saturn were undergoing migration, disrupting the orbits of numerous smaller bodies in the Kuiper belt and asteroid belt. As a consequence, these smaller objects were thrown into unpredictable paths, with many making their way into the inner solar system. This influx led to a significant rise in impacts on the terrestrial planets, including Earth. While these collisions did not involve direct clashes between planets, they illustrate how gravitational interactions can bring about substantial changes in the trajectories of celestial bodies. This bombardment is thought to have played a crucial role in shaping the surfaces and geological histories of planets in our solar system. Additionally, it may have contributed to the delivery of water and organic materials to Earth, influencing the development of our planet over an extended period. As stars go through changes in mass, flows then parts of planets around them may wind and potentially cross. This is particularly noticeable in systems where stars are at the end of their life cycle. As a star gets older and consumes its nuclear fuel, it often undergoes significant mass changes, especially during stages like the red giant phase or when it releases material in a planetary nebula. These variations in stellar mass can significantly impact the gravitational balance of the system, causing the orbits of nearby planets to either move outward or become more compressed. This is more likely to happen in multi-star systems, where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, exacerbating orbital shift and increasing the chances of orbits intersecting. This can result in situations where planets might get captured by another star, collide with other celestial bodies, or even get ejected into interstellar space. Pluto's unique orbit, initially acknowledged as a full-fledged member of the Planetary family, underwent a reclassification, ultimately being designated as a dwarf planet, owing to its distinct orbit. The astrophysics community is still enthralled by it and finds it fascinating. Even with this modification, there's cause for concern regarding the closeness of Pluto's track to Neptune's. According to recent forecasts made by eminent scientists like Neil deGrasse Tyson and Michio Kaku, these scientists are sounding the alarm about a grave danger to Earth, the possibility of a collision between the planets. Pluto is unlike any other planet in our solar system, and this is what makes its orbit around the Sun so unique. Pluto has not finished a full revolution since its discovery in 1930, and its orbit spans an extended 248 years. The fact that it deviates significantly from the roughly circular orbit of the big planets makes its course extremely elliptical, further adding to its fascination. Pluto also has a steeper orbit than the other planets because its inclination to the ecliptic plane is 17 degrees. Adding intricacy to Pluto's orbital pattern is the combination of its elliptical form and inclination. The point where Pluto's orbit crosses paths with Neptune's is an interesting feature. During approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging expectations based on their respective positions in the solar system. This prompts the question, why hasn't a collision between Pluto and Neptune occurred? The explanation lies in the gravitational influences exerted by other planets. The examination of Pluto's orbit commenced shortly after its discovery, presenting a puzzling trajectory for astronomers. Unlike the majority of planets whose orbits align relatively close to the ecliptic plane, Pluto's distinctive features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune, the three-body problem. Pluto's orbit remains stable amidst the intricacies, serving as a testament to the inherent complexities of celestial mechanics. Comprehending the motion and gravitational interactions of three heavenly bodies like Pluto, Neptune, and the Sun is known as the three-body problem in space. Predicting their trajectories from their starting positions and the effects of gravity on each other is similar for Pluto. Some of the terms that help to solve this astronomical mystery are azimuthal libration, latitude libration, and the VZK oscillation. According to astrophysicists, azimuthal libration is crucial because it keeps planets in their orbits. When Pluto crosses Neptune's orbit, it is at least 90 degrees distant, which is a critical distance that prevents collisions. According to this definition applied to Pluto and Neptune latitude libration, referring to the vertical movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is situated significantly above their orbital plane, providing an additional layer of protection against collisions. A key factor in understanding celestial motion is the VZK oscillation, named after three scientists, Van, Lee, and Kai. They explored the gravitational interactions between three space objects such as Pluto, Neptune, and the Sun. The VZK oscillation explains why Pluto's orbit around the Sun appears unusual but remains smooth over time, despite the apparent randomness in space. Underlying patterns and rules maintain order. These factors collectively stabilize Pluto's orbit, preventing collisions with Neptune or deviations from its course. The three-body problem helps us understand how the gravitational pulls of these space objects influence their path. Studying this contributes to our knowledge of Pluto, our solar system, and distant celestial bodies. Numerical simulations in the late 1980s revealed that despite stable properties, Pluto's orbit is technically chaotic, with minor initial deviations leading to significant differences over millions of years. Orbit stability. Nonetheless, Pluto's extraordinary orbit exhibits remarkable stability over extensive periods, effectively mitigating potential chaos. Recent computer simulations have deepened our comprehension of the intricate dynamics involving large planets such as Neptune, Jupiter, and Saturn influencing Pluto's trajectory around the Sun. Neptune's distinct gravitational influence, completing 3 orbits for every 2 of Pluto, significantly contributes to the overall stability of Pluto's orbital path. Jupiter's gravity is likewise important, though less so than Saturn's. Taken as a whole, all these observations demonstrate that Pluto is in secure and steady motion across space. Over billions of years, it is guaranteed by the combined influence of Jupiter, Saturn, and Neptune to keep the motions of celestial bodies in the universe ordered and predictable. These occurrences are essential. In the absence of these systems, the solar system would be more chaotic and unpredictable, increasing the likelihood of collisions and ejections from otherwise steady courses, which might have far-reaching consequences for other celestial bodies. In light of recent speculation regarding an eventual collision between Pluto and Neptune, it is essential to comprehend Pluto's orbit. With this information, the ever-changing solar system may be better grasped. The case of Pluto illustrates how the complex interaction between orbital mechanics and gravitational forces may cause apparently unstable orbits to achieve equilibrium. To better understand our place in the universe, it is crucial to continuously observe and analyze these events. Space exploration frequently exposes the erratic behavior of heavenly bodies. Pluto's orbit is a classic illustration of this erratic behavior. The example of Pluto provides a striking illustration of the idea of orbital chaos, which shows how the trajectory of a celestial body is highly dependent on its starting point. Minor shifts in the dwarf planet's location or speed can have a big impact on its orbital path over the long run. Scientists' understanding of Pluto's motion in space is mostly due to computer simulations. In order to simulate the gravitational interactions between Pluto and other planetary bodies like Neptune, these simulations employ intricate mathematical models. Astronomers can see how tiny changes can significantly affect Pluto's path by manipulating the models. These models uncovered a fascinating part of Pluto's trajectory in the late 80s. The orbit of Pluto can still be somewhat unpredictable, even though it is stabilized by features like azimuthal and latitude libration. When Pluto's position or velocity is somewhat off from the start, it can alter its course significantly over the course of several years. Even while Pluto's orbit is inherently chaotic, it stays stable for a very long time, billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows a structured order. Predicting cosmic events, especially with planets like Pluto that have unpredictable orbits, is quite challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Numerical simulations help us understand and anticipate the future paths of celestial bodies, but they also reveal the limits of our predictive abilities. These models heavily depend on accurate initial conditions and simulate complex interactions. Even a small error can lead to significantly different outcomes, making precise predictions difficult. The chaotic nature of celestial orbits, such as Pluto, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational influences of giant planets on Pluto's orbit gives valuable insights into the broader dynamics of the solar system. It demonstrates how each planet's presence and position can affect the stability and trajectory of other bodies in the system. Concerns of a potential collision, Neil deGrasse Tyson, a renowned astrophysicist pivotal in popularizing astronomy, offers a distinctive perspective on the enigmas within our solar system, particularly focusing on Pluto. Tyson, notable for reclassifying Pluto from a full-fledged planet to a dwarf planet, shares insightful reflections on the evolving nature of our understanding of celestial mechanics and humanity's enduring fascination with the unexplored realms of space. Rather than viewing Pluto's reclassification as a demotion, Tyson sees it as a necessary adjustment aligning with the expanding knowledge about the myriad objects orbiting the Sun. His approach to celestial mechanics centers around perpetual learning and adaptation. Tyson perceives the intricacies of orbits, exemplified by Pluto's unique path, as a constant reminder of the vastness of knowledge waiting to be unearthed in space. He asserts that the aura of these cosmic unknowns is the driving force behind the captivating nature of astronomy. Tyson also acknowledges the pivotal role of space-related events and discoveries in shaping public interest in astronomy. He considers incidents like Pluto's reclassification and its unconventional orbit as opportunities to ignite the public's imagination and curiosity about the universe. By delving into the dynamic and sometimes counterintuitive facets of space mechanics, Tyson opens a gateway for the general public to marvel at the wonders and mysteries of the cosmos. Working alongside other scientists, Tyson is actively cautioning the public about the potential danger of Pluto's unpredictable path. After studying Pluto extensively, he has raised concerns that the three-body problem might pose a real threat, suggesting that a collision with Neptune is long overdue. Additionally, he emphasizes how such a collision could disrupt the balance of the universe and lead to catastrophic consequences extending to Earth. A collision between Pluto and Neptune would be an unusual and catastrophic event in our solar system. This collision would release a massive amount of energy, likely breaking apart Pluto due to its smaller size and icy composition. Debris from the collision could scatter across the solar system, posing potential hazards for other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku's perspective. Michio Kaku, a distinguished theoretical physicist renowned for his contributions to string theory and science popularization, brings a distinctive perspective to the unfolding scenario. His insights into the future of space exploration and the intrinsic connection between celestial mechanics and theoretical physics offer profound reflections on phenomena such as Pluto's orbit. Kaku perceives the study of Pluto and its orbit as a window into the perspective realms of space exploration. According to him, unraveling the intricate gravitational interactions and orbital dynamics of celestial bodies, exemplified by Pluto, provides invaluable insights for forthcoming space missions. This acquired knowledge becomes instrumental in navigating the solar system, adeptly foreseeing potential hazards and strategically planning missions to the outer reaches of our solar system and beyond. Highlighting that lessons extracted from the scrutiny of Pluto's orbit can serve as a blueprint for approaching and understanding other distant celestial bodies. Kaku emphasizes the broader applications of this knowledge in his discussions on planetary physics. Kaku consistently underscores the profound interconnection between celestial mechanics and theoretical physics. He contends that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, aren't isolated occurrences but rather intricately tied to fundamental principles of physics. Kaku's pursuits in theoretical physics, particularly in the realm of string theory, aimed to fathom these principles at the most fundamental level. He posits that delving into the complexities of celestial mechanics exemplified by the orbit of Pluto has the potential to unveil insights into the underlying laws governing the universe, similar to Tyson. Kaku delves into the cosmic potentiality of a collision, seamlessly weaving it into his broader theories about the universe. If Pluto and Neptune were to collide, it would be a significant event in astrophysics, offering a unique observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework replacing point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. A collision of such magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme conditions, a key focus in string theory. Additionally, the gravitational waves produced by the collision could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Conclusion: Pluto's orbit serves as a remarkable example of celestial mechanics, showcasing both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. In all these envisioned scenarios, the actual probability of a planetary collision remains exceedingly remote. The sheer expanse of space, coupled with the relatively diminutive size of celestial bodies, renders direct collisions rare occurrences. Nevertheless, these hypothetical situations captivate the attention of astronomers and astrophysicists, serving as valuable windows into the dynamics of planetary systems and the evolutionary tapestry of the galaxy. The ongoing exploration of Pluto's orbit stands as a continual quest for knowledge within the realm of space exploration. As illustrated by Tyson and Kaku, each revelation propels us closer to unraveling the intricate fabric of our universe. It's a journey that not only challenges our existing perceptions but also broadens our horizons, laying the groundwork to inspire future generations of explorers and scientists. The allure of the cosmos, with its mysteries and potentialities, beckons us forward on a path of discovery and understanding. As we conclude our cosmic journey into the potential collision between Pluto and Neptune, it's essential to recognize that this astronomical rendezvous remains a distant possibility. Yet, the mere contemplation of such an event unveils the inherently unpredictable nature of space. Our exploration has taken us from the peculiar orbits of distant planets to the dynamic interplay of galaxies colliding. As we continue to gaze into the cosmos, who knows what other surprises await us?